In this video, we are going to study linear systems, its solutions and geometric interpretations. So why we study linear systems? Because linear system helps us to solve many practical problems in science, technology and day-to-day life. So let us go through some of them. When you are navigating a place through a map, when you are finding intersection points of two road maps, it is actually a solution of a linear system. And again in finance, when they are balancing budgets with multiple expenses and income, so there need to be a balance between expenses and income, we will use linear systems. And when we consider the nutrition value of many food items, so combination of which food items gives the optimum nutritional value, which is again a problem of this kind. And in engineering and electrical networks, traffic flow analysis, there are linear systems are using. And in modern world in data science, machine learning, algorithms and statistical modeling, again linear systems are using. So linear systems using everywhere. That is why we study linear systems in detail. So let us see one simple example. Here, this is a shopping problem. Suppose you visit a shop and you have two sets of information. 2 pens and 3 notebooks cost 50 rupees and 1 pen and 2 notebooks cost 30 rupees. So about the prices of pens and notebooks, you have two pieces of information. The first question is, can you find the price of each of them? As we know to solve such systems or such situations. So we can readily rewrite that situation into a mathematical form by assuming that x1 is the price of the pen and x2 is the price of the notebook. Then we can write the above situation of 2 pens and 3 notebooks is equal to 50 rupees as 2x1 plus 3x2 is equal to 50. And 1 pen and 2 notebooks is equal to 30 rupees as x1 plus 2x2 is equal to 30. So first above is a real life situations and below its mathematical model. One situation and one model. One practical situation and one mathematical model. This model is linear. So such a system is called a linear system. So let us see some example. In a linear system, why it is linear? Because each variable appear to the first power only. That is, no multiplication between variables like x1 into x2. No. Again, no nonlinear functions like logarithmic function sin x or exponential function, square root, squaring, nothing. Only the variable comes in a purest form or a linear form. Here I gave two examples for linear systems. One example for linear system and other for non-linear. The linear is 2x1 plus 3y equal to 5 and x minus 4y equal to 1. But look at the non-linear system. There square of x is there, x square, that makes it non-linear. Again, look at the second equation, there is xy. There also it is non-linear because x is multiplied by y. This is not possible in a linear system. So let us see the general form of the linear system where m equations in n unknowns. The unknowns are x1, x2, etc. xn. So how can we write them? It is a11 x1 plus a12 x2 plus etc. a1 and xn. Those a1, a11, a12 These are all numbers. The second equation is a21x1 plus etc. a22x2 etc. a2nxn. Those are again numbers. The mth equation is am1x1 plus am2x2 plus etc. amnxn equal to bn, where aij are coefficients. They are known numbers. They are the numbers in the equation. And bi is again a constant, which is the right hand side of the equation. And xj are variables that we need to find. So this is a general form of linear system of equation with n unknowns and m equations. Now let us see how it geometrically looked like. See the two-dimensional case where m is equal to n is equal to 2, that is 2 equations and 2 unknowns. It is like a11x1 plus a12x2 is equal to b1, a21x1 plus a22x2 is equal to b2. Here the geometric interpretation is each equation, here we have two equations, each equation represents a straight line in the two-dimensional space or plane. And what is their solution? Their solution will be the meeting point of those two lines. So each equations are lines, their meeting points is the solution. So when two lines come into action, we have three possible scenarios. Number one, the lines intersect exactly one point. Then the system is said to have a unique solution. That solution will be that meeting point. Case 2 is the lines can be parallel. There is no meeting point. That means there is no solution for the system. In such cases, that system is called an inconsistent system. And the third case is lines coincide. That is one line on the other line. They are the same line essentially. One line and the second line is on the first line. That means all the points in the line are solutions. So there are infinite number of solutions. These three cases arise when two lines draw on a plane or a paper. So let us look those scenarios. Here in this example I have drawn two lines. Line 1 which is in blue line, that is 2x1 minus x2 equal to 0. Second line is orange line, that is x1 plus x2 is equal to 3. Look at the meeting point red, where two lines are meet. That point is point 1, 2. This point is a solution of the system of these two lines. Then what about the case of no solutions? The lines above me and below me, they are parallel, they never meet. That means there is no solution. The lines are blue lines is x1 plus x2 is equal to 2, which is above line, and the second below line is x1 plus x2 is equal to 0. They never meet. So there is no solution. This kind of system is called an inconsistent system. Now comes the case where there are infinitely many solutions. Here one line is on the other line. The two lines are same. So that means all the points, some of the points are marked in green dots, all the points are what? Solutions. That is, there is infinite number of solutions. They are coincident line. That is, every point on that is a solution. In these cases, one line will be a multiple of the other line. So both lines are here x1 plus x2 is equal to 2. The second line maybe look like 2x1 plus 2x2 is equal to 4, or maybe 8x1 plus 8x2 is equal to 16, or even 3x1 plus 3x2 is equal to 6. That is, the line on the other line means one line is a multiple of the other. So all the green dot points are solutions. So what about the three-dimensional case? Then each equations become planes. When the three planes meet at a single point, that point is said to have the solution, the unique solution of the systems. Here we have three planes, that means three equations. The three equations meet at where? One point. That one point is a solution. That is a unique solution. Only one point is there. When two planes or three planes, when they meet at a line, planes can meet at a line. Like here I represent two lines. One is two planes. One is a green plane and the other one is an orange plane. They meet at a line. That is a red line. So when the things comes like this, all the points on that line, all the points on that red line are what? Solutions. And there is infinite number of solutions in this case. Look at this case. Here the three planes are there, but the three planes never meet at a single point. So what happens then? There is no solutions. So in this three-dimensional case also we have three scenarios. First one is unique solution, second one is infinite number of solution, or the third one is no solution. So three cases arise in both in 2 dimension and in 3 dimension. And let us see one of the special cases. Suppose what if I take all the right hand sides are zeros, that is b1, b2, etc. bn are zeros. This kind of system is called homogeneous system. It geometrically means that all the planes or all the lines passing through the origin. So everything comes to the origin, everything comes to the middle point 0, 0 of the plane. That is homogeneity. Such a system is called a homogeneous system. Its properties are, it has always a trivial solution. That means every plane and every line passes through the origin, means there will be one solution. We are sure about that. That is 0, 0, 0, 0 will be a solution. So in the homogeneous case, there is no case of no solutions. One solution is there. So there will be always a solution. Maybe other solutions also be there. This is a special case where it is called homogeneous system of equations. Okay, this general form we write a1 x1 plus a2 x2 plus etc. an xn, am1 x1 plus am2 etc. amn x1. What happens when the number of equations are huge, like 1 log, 2 log, and the number of variables are huge, like 1000, 10,000? Then we will get a huge matrix. So it is not easy to represent those in a real form. So we cannot handle those equations with that notation. So we will go for a new notation for that. It is ax is equal to b. We will collect all the coefficient numbers into a matrix and pack it in that matrix. And on the right hand side we write the unknown numbers x1, x2, etc. And on the right hand side we write like this b1, b2, etc. bn. So this aligns to a good beautiful form of matrix of all coefficient a11, a12, etc. a1n, am1, am2, etc. amn, and multiplied by the column matrix of variables x1, x2, etc. xn is equal to b1, b2, etc. bn. Then what about the capital A? It will be a coefficient matrix. Its size is m by n matrix. What about x? It is an unknown vector whose size is n by 1 matrix. Against what about the b? It is a constant vector whose size is m by n. So the matrix form of the linear system is ax is equal to b. Now what is augmented matrix? Augmented matrix is a matrix. We have a matrix A of coefficient. We just add those the column b1, b2, etc. bn with this matrix. We just take that column and paste here with this matrix. So we get a larger matrix having one extra column. That column is b1, b2, etc. bn. Because it is an extra column, we take it from outside. To represent that, we will keep a horizontal line between this. So this larger matrix is called the augmented matrix. We represent it by a tilde. So that vertical line separates the coefficient matrix and the constant, right hand side constant. So actually writing this augmented matrix form is a starting point of the solution of the system of equations, which we will consider in the next video lecture. So this is augmented matrix. So when we encounter a system of equation, what are the basic thoughts we should have in our mind? First one is, does there a solution exist? Is there any solution there? That is the first question. Mathematically, what it is called is the system is consistent or inconsistent. The second question about the system is about the uniqueness. If the solution exists, is that solution is unique? That is, all the planes, all the lines, or the hyperplane meet at a single point, or there are more than one solutions, or there are infinitely many solutions. And the third question is how we can solve this system. What is a computational technique to solve the system? To solve the system means to find all those values of x1, x2, etc., xn. Which computational techniques we will take? So these three questions should come in our mind when we encounter or when we see a system of linear equations. So our answer for the third question, that is what computational technique we will take the computational techniques of Gauss elimination method that we will cover in the next video lecture. So what we have studied today in this lecture is, there are 4 things we have studied. 1, linear system model countless real world problems, like what I said, navigation problems, finance, engineering, data science, AI, whatnot. Point number 2, each equation has a clear geometric interpretation. There may be lines in 2 dimension, planes in 3 dimension, or higher dimensions we call hyperplanes in n dimension. And the third point is, exactly 3 kinds of situations arise. 1, the system may have a unique solution, or the system does not have any solution, inconsistent, or there may be infinitely many solutions. And the fourth is a notation. When the system becomes larger, we can represent it as a compact form, a matrix form, which is Ax is equal to B, where A is the coefficient matrix, X is the unknown variable matrix, and B is the right hand side matrix. So this is all about system of linear equations and its geometrical interpretation. If you have any doubt, you can ask me directly or you can comment below. Thank you for listening.